interaction between the interaction or attraction. In fact, whenever the dipoles interact, they always attract each other. The attraction between the dipoles. The attraction between the dipoles is termed dipole-dipole interaction. Okay?
Yes, sir.
It is a significant intermolecular. It's a significant intermolecular attractive force. That's what we term as dipole-dipole interaction.
Sir, I'll just come in a second.
Sure.
Yes, sir.
Okay. So we have just write about the dipole and the dipole-dipole interaction. Now, having talked about this dipole-dipole interaction, let's get along with when we are talking about dipoles, we would consider that the dipoles are going to be the strongest when they have the maximum charge separation and they have the longest bond length. But what we
Yes,
find
sir.
is that if we have we want the charge separation, then in that case, the charge separation would mean that they are going to have a large electronegativity difference. Having a large electronegativity difference would mean that rather than being a strong dipole, the substance is going to become ionic. It's going to become an ionic bond. What we wish is that the bond remains covalent, but it has a high dipole moment. And this is something like an opposing fact. The species involved, one must be having a very high electronegativity, while other should have a low electronegativity. While the one with a low electronegativity should have a high ionization energy. Then only the bond would remain covalent and it is going to have a high dipole moment. Got it?
Yes, sir.
Now these opposing requirements are met only by one element, and that one element which meets these requirements is hydrogen. Hydrogen has a low electronegativity, it has a low effective nuclear charge, but it has a very high ionization energy. In fact, the ionization energy of hydrogen is even greater than that of chlorine. So if hydrogen is attached to extremely electronegative atoms like fluorine, or maybe oxygen, or maybe nitrogen, then this hydrogen is going to have a substantial positive charge. This dipole is going to be extremely strong. So much so that this dipole all becomes a weak covalent bond. But here, the species which can form the bonds with this hydrogen should also be having a very high negative charge, and it must have at least a lone pair. And this condition may be met by fluorine, oxygen, nitrogen, or in this case, chlorine. This interaction between hydrogen attached to a very electronegative atom and an atom having a very high negative charge and at least a lone pair is called the hydrogen bond. So write the definition. Write the definition.
Yes, sir.
The interaction between a hydrogen, the interaction between a hydrogen attached to the interaction between a hydrogen attached to a very electronegative atom, the interaction between a hydrogen attached to a very electronegative atom, such as fluorine, oxygen, or nitrogen, such as fluorine, oxygen, or nitrogen, and and an atom and an atom having a very high negative charge and an atom having a very high negative charge and at least very high negative charge and at least one lone pair, at least one lone pair is termed hydrogen bond. Full stop. It is stronger. It is stronger than it is stronger than a normal dipole-dipole. It is stronger than a normal dipole-dipole interaction, but much weaker than an actual covalent bond.
Yes, sir.
Clear? Full stop. Further, due to involvement, due to involvement of a lone pair, due to involvement of a lone pair, the hydrogen bond is directional. It is formed in a specific direction.
Sir, how is it directional?
See, when we talk about the lone pair around an atom is in a specific direction. Specific electron pair is there. Specific orbitals are there. So the hydrogen bond is going to be formed in that particular direction. For example, let us say we talk about the hydrogen bond formed in water. When you talk about water, water has such a kind of a structure. It's a bent structure here. So this is the structure of water. Now this water oxygen has two lone pairs. Let's say we have another water molecule. This water molecule here, it's going to have hydrogen. Here it's going to have hydrogen. And here it's going to be having the electron pairs. Here again, we have another water molecules, oxygen, hydrogen, and hydrogen. Now what happens is that these water molecules, they form hydrogen bond. This is the hydrogen bond between them. What we find is that there is another water molecule moving towards it here. Now oxygen has electron pairs here. Now what happens is that when water molecule is moving towards this place, these hydrogens, they suggest to the oxygen, or rather they ask the oxygen, that would you like to form a bond with us? The system is absolutely certain of certain things. That is, system asks, do we have high energy in the system or low energy in the system? If we have high energy in the system, we are not going to form the bonds because bonds are going to make the energy of the system even higher. But if we have the system with low energy, then in that case, it would like to release the energy and switch off the gap of that energy. It's going to release some energy. That could be said that whether we have a high temperature or low temperature. If we have a low temperature, then bond formation would be favored. But if we have a high temperature, bond breaking would be favored. So let us say if we have a low temperature, then in that case, this water molecule would expect to form the bond. But here, since the hydrogen bond can be formed only in a specific direction, they can't be formed anywhere. This water molecule has to stop here. If it moves further, it won't be able to make the hydrogen bond. So to make the hydrogen bond, the water molecule stops here. The hydrogen bonds are formed here. So it is a particular direction, at a particular position, at a particular distance, and that is how it appears to be a covalent bond. Now, because of the formation of the hydrogen bond here, we find that it becomes an open cage with an empty space.
So, but how will four water molecules bond, or what will be the formula? 4H2O.
It's not a formula, it's not a 4H2, it is going to be an entire network, a three-dimensional network of water molecules. And that three-dimensional network of water molecules is what we term as ice.
Oh,
And because of this empty space, this ice is going to occupy a much larger volume. Now, we have this ice having empty space in it. Now we melt the ice. When we melt the ice, we provided the energy. When we provide the energy, some of the bonds are going to break. When some of the bonds are going to break, the water molecules are going to move closer to each other. When they are going to
yes,
move
sir.
closer to each other, the emptiness is going to decrease. And what we find is that liquid water, because of this lack of empty space, has a higher density compared to ice.
So, can you tell the last part again?
I said that due to less empty space, the liquid water has a higher density compared to ice at the melting point.
Yes, sir. Okay.
Okay. Now, if we increase the temperature further, even more hydrogen bonds break and water further contracts. But this goes on only till 4 degrees Celsius, beyond which the increase in kinetic energy is able to compensate for the decrease in bonds, decrease in spaces. And therefore, we find water has the highest density at 4 degrees Celsius. Is that clear?
Yes, sir.
So that's what we have as the effect of hydrogen bond in case of water. Now, when you talk about the hydrogen bonds are classified in two categories. One is called intermolecular, and the second one is called intramolecular. The intermolecular and intramolecular. Intermolecular are very obvious to see. This is what we have as intermolecular, different molecules, they are forming the bonds. These intermolecular hydrogen bonds have certain outcomes. First of all, they make the structure a bit stronger and difficult to separate out. So intermolecular hydrogen bonds are something which increase the melting point and increase the boiling point. They make the breaking of the substance a bit difficult. So intermolecular hydrogen bonds, they increase the melting and boiling point of the substance. The examples are a lot many. Something like we have, we are going to talk about it later. Like we have HF. HF is going to have a much higher boiling point as compared to what it should be. Similarly, water. Water is going to have a higher boiling point as compared to what is predicted by the Dipole-Dipole interaction. So that's what we have as intermolecular hydrogen bond. Then we have another case, and that is what we call as intramolecular hydrogen bond. Intramolecular hydrogen bond is something like in orthonitrophenol. This is orthonitrophenol. Here, there is a hydrogen bond between oxygen and hydrogen. This is what we call as intramolecular hydrogen bonding, and the name is orthonitrophenol.
So what are the edges? Are they carbon?
Yeah, these are all carbons. This is carbon,
Okay.
this is carbon, this is carbon. This is a benzene ring.
Yeah.
Okay. Then another one, it could be what we call as orthohydroxybenzaldehyde. This has another name, salicylaldehyde. Salicylaldehyde. So this is orthohydroxybenzaldehyde. This is what we have as orthonitrophenol.
Yes, sir. Done.
Okay. So this is what we have as intramolecular hydrogen bond. And because of this intramolecular hydrogen bond, these species actually have a lower melting and boiling point than what it should be. So these have lower melting and boiling point. The intramolecular hydrogen bonding has exactly an opposite effect as compared to intermolecular hydrogen bonding. Now there's a little trick question. Rohan, could you tell me about something which is actually a proper liquid, but it becomes a solid when you heat it?
Sir, if you heat it, the kinetic energy will increase and the bonds will break, so it should become
A
gas, right? How
liquid.
will it become?
That's what I'm asking you. Can you tell me something about a substance? There is a substance which becomes a solid when it is heated. It's actually a liquid before. And it's a very common substance. Everybody knows about it.
Oh, sir, what?
That's what I'm asking.
I don't know.
The answer is an egg.
Oh yeah, an egg.
If you heat an egg, do you have eggs?
Yes, sir.
So I believe you would be knowing very clearly that whatever way you heat it, the egg always solidifies when heated. We call it
Yeah.
coagulation, we call it denaturation, but the fact remains that it solidifies. Can you give me a reason why the egg solidifies when heated?
So it's intramolecular, so the bonds get stronger or something.
Now, in case of egg, it contains proteins. The proteins are joined together by intramolecular hydrogen bonding.
Oh, okay.
And when it is heated, the intramolecular hydrogen bond break, and while they are breaking, they join with other molecules. It becomes inter. The intra becomes inter.
Okay.
Okay.
Yes,
A-
sir.
And that is how it becomes the solid.
Solid.
Clear? So you have got the
Yeah.
difference between intra and inter hydrogen bondings?
Yes, sir.
Okay. Now, Rohan, uh, that's what we are going to do about hydrogen bond, and we are going to deal with it a little later. Could you please tell me what exactly is going on in Fiji at the moment?
So they start H bond.
They just started H bond.
Yeah.
Okay. Did they do dipole-dipole interaction first?
So they're doing it now, I think. After they do H bond or something.
Mm-hmm.
Deep by something like that is there.
Deepa?
Yeah, that's what the other classes said. But in our class, we were actually a little behind because our chemistry teacher was absent for a few days.
Mm-hmm. So what
So we
exactly
have to
are
do
you
H
doing?
bond. We are doing H bond.
Okay, fine. So now let's get a little further. We have just talked about the hydrogen bonding. We have talked about the condition of hydrogen bonding, and you are supposed to remember these conditions. Okay, these are
Yes,
important
sir.
ones. Now, Rohan, I would like to ask a very simple question from you. Very, very simple question.
Yes, sir.
Let us say we have two helium atoms. There is another one helium atom. There is another helium atom. These are the two helium atoms with the nucleus and electron cloud around it. Is there any reason that the two helium atoms are going to attract each other?
No, sir. They should repel because electrons are in the front.
Fine enough. So if the helium atoms are going to repel, do you think helium is going to liquefy? For
No,
anything
sir.
to liquefy, the attractive forces must overcome the thermal motion. Then only the substance is going to liquefy. Otherwise, it's not going to.
Yes, sir.
Okay. So do you think helium is going to liquefy?
No, sir.
Okay. Rohan, did you hear about Chandrayaan?
Yeah. Yes, sir.
You know that initially its launch was aborted.
Sir, I know it failed. I didn't know what about it.
Fine. It failed later when it actually landed on moon. Then it failed.
Yes, sir.
But initially also, it was actually initially aborted and it was launched at a later date.
Okay.
So I believe you don't have any idea why that launch was actually aborted.
No, sir.
See, in Chandrayaan, they were using cryogenic engines. Cryogenic engines are the ones which contain liquid hydrogen as the fuel and liquid oxygen as the oxidizing agent, as a supporter of combustion.
Yes, sir.
So that liquid hydrogen is a fuel and liquid oxygen is a supporter of combustion. Now this Chandrayaan, this liquid hydrogen has to be maintained at a pressure. Now, hydrogen liquefies at such a low temperature that everything in liquid hydrogen is going to become a solid. It won't be able to maintain the pressure. But helium is the only thing which remains a gas even at liquid hydrogen temperature. So helium was used to maintain the pressure in the hydrogen cylinder. The problem was one of the helium tanks developed a leak and that needed to be replaced. So that was Chandrayaan. That was the helium. So helium doesn't liquefy easily. But the problem is helium also does liquefy, although at a very low temperature of something like 4.2 Kelvin, minus 269 degrees Celsius, but it does liquefy. So it simply
Yes, sir.
tells us that although the helium-helium atoms have the least attractive force between them, they still do have some force between them. What could be the reason for helium atoms to have attractive force between them?
So the nucleus attracts the electrons of the other atom.
Well, it's not the attraction of the nuclei. Nuclei also are going to repel each other. The atoms are also going to repel each other. What could be the reason? The reason would be a very peculiar one. Did we talk about something called polarization?
Yeah, yes, sir.
Okay. Now we are going to talk about something called the polarizability. Write the definition, polarizability. The ease with which, the ease with which a species, the ease with which a species can be polarized. It is termed polarizability. Okay, full stop. Polarizability increases. Polarizability increases if the outer electrons, if the outer electrons are loosely held, are loosely held. Full stop. Hence, if a species has, hence, if a species has a large surface area, a species has a large surface area, it is more polarizable. Okay,
Yes, sir.
clear? Full stop. A high effective nuclear charge, a high effective nuclear charge and a smaller size reduces reduces the polarizability. Reduces the polarizability. Fine. Now, when we talk about helium, helium has an extremely small surface area. It has an extremely high charge. So when we talk about helium, it is extremely difficult to polarize helium, but it's not impossible. Helium can get polarized a bit, maybe for an instant. And if it gets polarized for a bit, even for an instant, for that instant can polarize another helium atom. Now these two are temporary dipoles.
So what is this dotted line?
This is the polarized structure that has formed.
Okay.
The deformation of the electron cloud of helium. Now helium has an extremely small surface area, and because of that, its polarizability also is extremely low. So helium would be extremely difficult to polarize. The temporary dipole interaction would be extremely low, and that is why helium is very difficult to liquefy. Now this interaction between temporary dipoles due to the dispersion of the electron cloud is termed as dispersion forces. It is termed as dispersion forces. It is termed as London forces and come under category of weak van der Waals forces. Okay.
Yes. Yes,
So
sir.
let's write the definition of London forces or dispersion forces. London forces or dispersion forces. The interaction between two temporary dipoles the interaction between two temporary dipoles is termed dispersion force or the London forces. Dispersion forces or the London forces. Okay?
Yes,
Is that
sir.
clear? Now these London forces, dispersion forces, as obvious, depend on surface area. More becomes the surface area, more are these going to be the attractive forces. Now let us see what these attractive forces do and how they change with the surface area. Let's get along with very simple facts. We have helium, we have neon, we have argon, we have krypton, we have xenon. Now amongst these noble gases, which do you think would be having the highest melting and boiling point?
Sir, xenon.
Perfect. Xenon has the highest surface area, and that's why it should be having the highest melting and boiling point. Now let's talk about halogens. We have fluorine, we have chlorine, we have bromine, and we have iodine. Now what we find is that halogens do not exist as FCl, Br, and I. They exist as F2, Cl2, Br2, and I2. If we have
Yes,
two
sir.
atoms, the surface area increases significantly. So what we observe is fluorine is a proper gas. Chlorine is an easily liquefiable gas. Bromine is a liquid, while iodine is a solid. So as you can very well see, as the size is increasing, the melting and boiling point increases.
Yes, sir.
Now, let's get along with some important questions. We have HF, we have HCl, we have HBr, and we have HI. What could you say about the melting and the boiling point trend of these? Which is going to have the highest melting and the boiling point, while which is going to have the least?
Sir, HI should have the highest and HF the least.
The problem is HF has the highest.
Sir, intramolecular bonds. Yeah, sorry. Yeah.
Intermolecular hydrogen bond. I told you that HF shows a very high melting and boiling point, which should not be there. According to its surface area, it should be having a very low melting and boiling point, but HF has a very high melting and boiling point because it is capable of forming hydrogen bonds.
Yes, sir.
Is that clear?
Yeah. But sir, even HI is an intermolecular H bond, right?
HI cannot form the hydrogen bond because iodine is not electronegative enough to put a very high positive charge on hydrogen.
Oh,
I told you
okay.
that hydrogen must be attached to fluorine, oxygen, or nitrogen, which in this case it's not.
Yes, sir.
Okay, so the order actually turns out to be HF is the highest, then is HI,
Okay.
then HBr, HCl. HCl is the least, HF is the highest.
Yes, sir.
Okay, now what could you say about H2O, H2S, H2SC, H2T?
So the highest should be H2O.
Yes, it is. And the next is H2T. Clear?
Okay.
First is hydrogen
Yes.
bond, then we have the surface area. Is this clear?
Yes, sir.
So here we have just finished off with the weak van der Waals forces. Fine.
Yes, sir.
Now let's talk a little further. One more topic we talk about. Let's say we have an ionic compound. Ionic compound would mean we have the two ions. We have the cation, we have the anion.
Yes, sir.
Here we have the cation, and here we have the anion. Now, is it not quite obvious that anion is going to be much larger as compared to the cation? Because we have put
Yes,
an
sir.
electron into the anion and it would expand. The cation, we have actually removed the electron, it's going to contract. Now, amongst these two, which do you think, amongst the cation and anion, which do you think is going to be more polarizable?
Sir, no, the anion.
The anion is going to be more polarizable because it's going to have a larger surface area. It's going to have a less effective nuclear charge as it has expanded and it even has a negative charge. So anion is
Yes,
going
sir.
to be more polarizable. This cation practically is non-polarizable.
Okay.
Clear? Because cation actually has the species, it has a lower size, it has a higher effective nuclear charge, and so it is practically non-polarizable. Now for cation, we have another term. And that another term that we talk about is called polarizing power. Okay.
Yes, sir.
Polarizing power. Write the definition. The capacity of a species the capacity of a species to polarize the capacity of a species to polarize another species the capacity of a species to polarize another species is termed polarizing power. Polarizing power. Okay. A species with a high effective nuclear charge, a species with a high effective nuclear charge and high charge density, a species with a high effective nuclear charge and a high charge density has a high polarizing power.
Yes, sir.
Is that okay? That's
Yeah.
what we have as polarizing power. This is what we have as polarizability. So cation has a polarizing power and anion has a polarizability. Now, because of this polarizing power of the cation, the anion gets actually deformed. This is going to become like this. Now, the electron, which should have been centered only on the anion, now actually moves towards the cation and it's kind of shared between the two.
Yes, sir.
Okay. Due to the polarizing of the anion by the cation, the electron cloud moves between the cation and anion, that is, it's being shared between the cation and anion. And the sharing
So,
of the electrons between cation and anion would make this bond slightly covalent.
sir,
So
what is shade between the anion and cation?
see, the electron has shifted towards the cation while it should have been entirely towards the anion.
Yes, sir.
And if it has shifted towards the cation, then in that case, it has come in the region between the cation and anion.
Yes, sir.
So could we not say that it's being shared between the cation and anion?
Yeah.
And if it is being shared, then it becomes a covalent bond.
Yes, sir.
So polarization of the anion by the cation creates a covalent character in the ionic bond.
Okay.
Is that okay? So
Yes,
now,
sir.
a scientist whose name was Faience, actually the spelling is Fajan. It is not Fajan, it is Faience. But if you wish to call it Fajan, I don't care about it. This is
Yes, sir.
Faience rules. Faience rules allow us to find the covalent character in the ionic bond.
Okay.
Okay, so let's talk about the Faience rules. Write it. Faience
Yes, sir.
rules are the factors Faience rules are the factors which favor the covalent nature in the ionic bond. Factors which favor the covalent nature in the ionic bond.
Yes, sir.
The first one, small size the small size of the cation. That is the first one. Second, high charge of the cation. High charge of the cation. Third one, large size of the anion. Large size of the anion. High charge of the anion. And the fourth one,
So the third one was large size of the
of the
anion.
anion.
Yeah.
And the fourth one, non-noble gas, or pseudo non-noble gas or pseudo noble gas configuration. Non-noble gas or pseudo noble gas configuration of the cation. Okay. Now everything else is fine. I believe let's understand what exactly is meant by non-noble gas or pseudo-noble gas configuration. Let's have few cations. We have a cation called K plus. Another cation is Ag plus and another cation is Fe2 plus. Now K plus, potassium has an atomic number of 19, silver has atomic number of 47 and Fe has atomic number of 26. Could you write the outer shell configuration of each of these?
Yes, sir.
Write it.
So like 1s2, 2s2.
I just want outermost. If you want to write the complete, it's your wish.
Okay. So can I just open the door and come?
Sure, sure.
Yeah. So for potassium, it's 3s1.
Potassium is 3s1. What would be K plus? Potassium is not 3s1. Potassium is
Oh,
4s1.
yeah, yeah. So it's 3s6 for K plus,
3
S6.
P6. Rohan.
Yeah, yes, 3p6.
Mm-hmm.
So what would it be for Ag plus? It's quite long.
47 is the atomic number. Go ahead.
So for Fe2 plus, it's 3d4.
3d6. The electron goes out from the s orbital, not from the d.
Okay. So 5s.
5s? Which one has 5s?
Oh, sorry, Ag plus.
Ag plus.
3d10.
Ag plus is going to be d10.
Yeah, 4d10, sir.
So outermost of potassium is 3p6. Silver is 4d10 and iron is 3d6.
Yes, sir.
Is that clear? Now, as you can
Yeah.
see that potassium has a configuration of argon.
Yes, sir.
So potassium has a configuration of argon. But silver, although it is completely filled, it is not a noble gas configuration. It behaves like a noble gas configuration, but it is not one. Something which behaves like something it is not is called pseudo. So this is called pseudo noble gas configuration. This is pseudo noble gas configuration. Is that clear?
Yes, sir.
And while this one is what we call as a non-noble gas configuration. Non-noble gas configuration.
Yes, sir.
Is that clear?
Yes, sir.
So this is what we have as pseudo-noble gas configuration, and that's what we have as non-noble gas configuration.
Yes, sir.
Any confusions? Now, one
No,
thing you
sir.
can actually find out that this pseudo-noble gas configuration and non-noble gas configuration are going to have a higher effective nuclear charge as compared to the noble gas configuration.
Okay.
And that is why the transition metal compounds have a significantly higher covalent character compared to the representative elements compounds.
Yes, sir.
Is that clear?
Yes, sir.
Okay, Rohan. So the next class we are going to have on Sunday.
Yes, sir.
Okay. Are you